Look at this visualization of abstract data blocks assembling. It perfectly represents the reality of modern enterprise CI/CD pipelines. Development teams manage rapidly expanding wikis, and they have to constantly translate thousands of documentation points into highly structured work items. The standard approach to handling this volume is docs of code. Teams use nested folders of Markdown files to define their hierarchies, keeping their documentation right alongside their source code. But asking non-technical product managers or analysts to engage with raw Markdown creates immediate friction. They are forced to manually type out complex YAML front matter just to define metadata like dependencies, story points, or area paths. One missed indentation breaks the build. To parse those files safely, engineering teams build heavy backend infrastructure. They deploy Node.js or Express servers to read the raw text, run validation checks, and ultimately orchestrate the REST API payloads required by platforms like Azure DevOps. When you scale this traditional architecture across an entire enterprise, you create a bottleneck. Relying on dedicated backend servers to parse text files introduces network latency and adds unnecessary infrastructural overhead for tasks that amount to simple string manipulation, which forces us to ask, do we actually need the backend compiler at all? This diagram maps the data path. Left, the standard model uses a Node.js intermediary. Right, we eliminate the back office, routing logic to the browser. With React, the front end processes Markdown and executes API calls natively to the database. Making this shift requires solving two distinct technical challenges. First, we have to provide a rich UI experience that shields users from the syntax. Second, the browser must securely perform complex data mutations to satisfy enterprise platform security constraints. Migrating the parsing engine to the client side eliminates backend maintenance, while granting the front end absolute programmatic control over how the final data payload is structured. We start at the UI layer. The foundation of this front-end architecture is the Monaco editor, the same engine that powers VS Code. Monaco is highly performant, but it has a specific limitation. It is strictly a code and text editor. It is not a native rich text environment like Word or a content-editable div. To bridge this gap, we build a snippet injection toolbar directly above the editor. As this split screen shows, the user gets a familiar formatting ribbon on top while the application renders the result in real time. The formatting ribbon operates programmatically. When a user highlights a string of text and clicks the Code button, the toolbar reads the cursor location and automatically wraps the highlighted segment in the correct Markdown backticks. Non-technical users interact with familiar buttons, bold, italic, headers, without ever needing to memorize Markdown syntax. We can map complex structures just as easily. A user clicks Task List in the sidebar, and the application instantly drops the exact bracketed syntax required for a checklist right at their cursor. Snippet injection provides the necessary illusion. It gives users the accessibility of a WYSIWYG editor, while allowing the application to generate the strictly formatted raw code required for the database. Generating the text is only the first step. The application still needs to validate complex YAML metadata, like ensuring an area path actually exists, before the user submits the file. Intelligent validation is typically handled by a language server protocol, or LSP. In a traditional setup, the editor sends keystrokes over a WebSocket connection to a backend server running the LSP, which then returns autocomplete suggestions. We eliminate the WebSocket requirement by using a package called Monaco-YAML. This allows us to run the YAML language server entirely inside a browser web worker, operating on a separate thread from the main UI. When the React app loads, it makes a single API call to fetch the valid ADO tags and area paths. It dynamically injects those arrays directly into the web worker's JSON schema object. By isolating the LSP in a web worker, the Monaco editor provides real-time validation, error hovering, and autocomplete for the hidden YAML fields entirely offline. Zero server connections required. Once the raw text is formatted and validated, the client-side application has to compile it. To read the document structure, we implement the Unified JS ecosystem. Unified JS provides isomorphic parsers. Because the logic is written in JavaScript, the exact same parsing engines that typically run on a Node.js server run flawlessly right inside the browser's JavaScript engine. The browser converts the raw Markdown into a Markdown abstract syntax tree. Every paragraph and heading becomes a distinct node. The application walks the tree, locating specific branches, isolating data nested under a single element like a Level 2 heading titled Acceptance Criteria. Targeting nodes based on their heading hierarchy is the prerequisite for database integration. It allows the compiler to separate the Markdown body into distinct chunks that align exactly with the discrete fields of an Azure DevOps work item. By manipulating the abstract syntax tree in memory, the front-end secures complete programmatic control over the document structure, relying entirely on local processing power. Having access to the AST is critical when we need to bypass rigid platform constraints. For example, Azure DevOps enforces strict cross-site scripting protections. If you send standard HTML checkboxes to an ADO rich text field, the platform's security filter automatically strips them out. To fix this, we instruct the browser to traverse the MDAST and isolate checklist nodes by querying for properties where the checked state is specifically Boolean. Look at this isolated AST node containing a Boolean checklist property. We intercept it before it ever becomes HTML. The application executes a Unicode swap, mutating the node into a standard list item prepended with a Unicode box character. ADO's sanitization process targets standard input tags, but it ignores text characters. The Unicode boxes easily survive the filter, rendering perfectly as visual checkboxes in the rich text field, but the visual representation is only half the requirement. Enterprise teams track metrics by turning these lists into discrete, assignable child work items. To accomplish both, we deploy a dual task strategy directly on the tree. As the application mutates the node for visual formatting, the raw text inside the checklist is simultaneously extracted and routed down a secondary pathway. The browser compiles these isolated text strings into a standalone JSON array, entirely separate from the document body. This resulting array maps directly to the ADO Relational API to programmatically generate individual child task work items linked to the parent. By intercepting and manipulating the AST node, a single user input securely populates a sanitized rich text field and establishes accurate relational database links at the same time. With the tree fully mutated and the data arrays extracted, we move to the final preparation phase, serializing the structure for transport. The application uses the remark rehype utility to convert the Markdown abstract syntax tree into a HAST, an HTML abstract syntax tree. This step ensures that complex document formatting is locked in place. If the user included syntax highlighting for C# or Python, it has to render accurately in the database. The parser maps those raw code blocks strictly into pre-formatted pre-code tags, guaranteeing platform compatibility across different enterprise systems. Finally, the application stringifies the HAST, collapsing the node structure into a raw, deployable HTML string. HAST conversion guarantees that the highly customized Markdown structure matches the strict HTML requirements of the enterprise work item fields. The browser now holds all the necessary pieces in memory. It just has to assemble them. This diagram shows the final assembly. The distinct data streams, the serialized HTML strings, and the extracted JSON arrays merge to construct a single JSON patch payload. The structured HTML maps perfectly to the system description and acceptance criteria fields, while the arrays define the hierarchical folder tree and task relationships. The React frontend executes the REST API call, firing the patch directly from the client to the Azure DevOps endpoints. We have successfully parsed the syntax, bypassed the security constraints, and structured the data relationships. This client-side pipeline achieves enterprise-grade deployment, removing the latency and maintenance of a dedicated backend server entirely.